Every star has a story, a journey that spans millions or even billions of years, from birth in the vast clouds of dust and gas to its final fate as a white dwarf, neutron star, or even a black hole. Stars live, shine, and eventually die, shaping the very fabric of the universe. This is the life of a star. Stars are born in stellar nurseries, massive clouds of gas and dust called nebulae. Gravity pulls these particles together, creating dense clumps. As these clumps grow, they heat up, forming what we call a protostar, a baby star in the making. As more gas falls in, pressure and temperature rise. When the core reaches about 10 million degrees Celsius, something incredible happens. Nuclear fusion ignites. This marks the birth of a real star. Fusion generates the energy that makes stars shine, and now, the star officially enters the main sequence stage. The process begins with the collapse of a region within a nebula, where gas particles start to swirl and clump together under gravity's pull. As the protostar forms, it often gathers an accretion disk of material spiraling in, feeding the growing star. Protostars can also exhibit powerful jets and outflows, expelling material back into space. Deep within the core, the temperature continues to rise, reaching the critical point for nuclear fusion. Fusion reactions begin, converting hydrogen into helium and releasing immense energy. This energy radiates outward, causing the star to shine brightly and marking its entry into the main sequence phase. Once nuclear fusion starts, the star settles into a balance between gravity pulling inward and fusion pushing outward. This is the main sequence phase, the longest period in a star's life. For our Sun, this phase lasts about 10 billion years. Smaller stars like red dwarfs burn fuel slowly and can live for trillions of years. Medium-sized stars like our Sun last billions of years, but massive stars, the blue giants, burn their fuel rapidly, living only a few million years. During the main sequence phase, stars convert hydrogen into helium in their cores through nuclear fusion. This process releases a tremendous amount of energy, which we perceive as the star's light and heat. The balance between gravitational forces and the outward pressure from fusion keeps the star stable. Different types of stars have different lifespans during the main sequence phase. Red dwarfs, the smallest stars, can remain in the main sequence for up to trillions of years. Stars like our Sun, which are medium-sized, spend around 10 billion years in this phase. Massive stars, such as blue giants, have much shorter main sequence phases lasting only a few million years. The main sequence phase is a period of stability, where stars shine steadily and maintain their structure. This phase is crucial for the development of planets and life, as it provides a consistent energy source. As the star runs out of hydrogen, fusion slows down. Gravity takes over, squeezing the core tighter. But this compression heats the core, allowing helium to fuse into heavier elements like carbon and oxygen. This makes the outer layers expand, turning the star into a red giant. This will be the fate of our Sun in about 5 billion years. It will grow so large that it could swallow Earth. For the biggest stars, the process is even more dramatic. They fuse heavier and heavier elements until iron forms. But iron fusion doesn't release energy, it absorbs it, and that's when things get really explosive. Before a star becomes a red giant, it goes through a series of changes. The core contracts and heats up, igniting helium fusion. This leads to a helium flash, a sudden burst of energy. The outer layers expand rapidly, and the star swells into a red giant. As it expands, the surface cools, giving it a reddish hue. In the case of massive stars, they evolve into supergiants. These supergiants continue fusing elements in their cores. Eventually they form an iron core, leading to their dramatic end. The iron core collapses, resulting in a supernova explosion. The remnants of this explosion scatter across the cosmos. These remnants can eventually lead to the birth of new stars. Smaller stars like the Sun peacefully shed their outer layers, creating beautiful planetary nebulae. What remains is a white dwarf, a super-dense, Earth-sized core that will cool down over billions of years. But for massive stars, the end is much more violent. The core collapses in an instant, triggering a supernova, one of the most powerful explosions in the universe. Supernovae spread elements like gold, iron, and oxygen into space, ingredients essential for life itself. What's left behind depends on the star's mass. If the core is about 1.4 times the mass of the Sun, it becomes a neutron star, an ultra-dense remnant where atoms are crushed into neutrons. But if the core is even bigger, it collapses beyond anything known, forming a black hole, a region so dense that not even light can escape. Neutron stars can also become pulsars, emitting beams of radiation as they spin rapidly. Black holes, on the other hand, can grow by consuming nearby matter, forming accretion disks and warping space around them. In some cases, black holes exist in binary systems, pulling material from their companion stars. When black holes merge, they create ripples in spacetime known as gravitational waves, detectable across the cosmos. Some supermassive black holes at the centers of galaxies become quasars, emitting powerful jets of energy. These supermassive black holes play a crucial role in the evolution of galaxies, influencing their structure and growth. But the death of one star brings the birth of another. The elements from old stars become the building blocks of new ones, continuing the endless cycle of stellar life and death. So the next time you look up at the stars, remember, you are looking at the past, the present, and the future of the universe itself. Thanks for watching.